All right, for this lecture, we're going to combine a couple other lectures again. So we're going to be talking about the refrigeration cycle, which is a little bit lengthy, and then measuring superheat and subcooling. I'm not going to get into much depth here. It's a little more for technicians and understanding how refrigerants work and how to measure that with pressure temperature relationships. So with the refrigeration cycle, let me pull that up here for you. So as we get into it here, I'll try to go through a lot of these basics really quickly for you, so you can get into more of the components of the cycle and understanding how it works to create refrigeration. So we talked about British thermal units before, right? So I don't need to go through that, but a ton of cooling is something that we need to address as well. And it's the amount of heat that's needed to melt a ton of ice over a 24-hour period. And the relationship there is 1 ton of cooling equals 12,000 BTUs per hour. So again, understanding how these different measurements come into play. Understanding different types of heat is important when it comes to refrigeration. We have sensible versus latent heat. So sensible is that heat that we feel. There's a change in temperature without change in any other variables. Those variables typically are pressure, volume, stuff like that. So this is what we are feeling when we are talking about temperature outside. Latent heat is a little bit different, right? It's an energy exchange. We're releasing or absorbing energy during a constant temperature process. So we have to have heat that's introduced that's required to convert something from a solid state to a liquid state to a vapor state. So the process of melting ice or water boiling. The reason why these are important is because as we are changing the state of matter, we need to have that latent heat, and that's what's going to help us create the cooling mechanism and the cooling process. Also important to understand these two terms, superheating and subcooling. So superheating is anything that is any temperature of a gas that is above the boiling point of the liquid. So, and then anything that's subcooling is any temperature of liquid below its boiling point. Not the greatest example or definition, but basically once we get to the point of, say, water, right? We're boiling water on a stove. Once it hits that 212 degrees Fahrenheit, we can no longer add heat to the water. The steam will boil off, and if we start adding heat to that steam, then we're superheating it. If we are cooling anything below that point of 212 degrees for water, then we are subcooling it from that point. When we're changing the state, we have either evaporating, right? We're picking up or absorbing heat. We're changing to a gas from a liquid. Condensing, again, a lot of refreshers, but giving off or rejecting heat. So we're changing back to a liquid. And then we have flash evaporation, right? So flash evaporation is a little bit different. It's a partial vaporization of a saturated liquid as the pressure is reduced as it's passing through a throttling device. And this comes into play as we start understanding how the refrigeration cycle works. When it comes to heat transfer, we have the use of refrigerants. Instead of using water for a lot of heat transfer and air conditioning purposes, we use refrigerants because they boil at low temperatures. They circulate through this closed loop. They send the liquid back and forth. They never wear out, technically. So they're a lot more efficient for larger applications than cooling with water. Also understanding pressure-temperature relationships. So as we increase pressure, we increase temperature and vice versa. So I can go through that. And then also the understanding that heat flows from warmer to cooler, right? So also meaning higher pressure to lower pressure. We have to, in order to create the cooling effect, we have to actually mechanically change the state. So that's why we use the flashing device, which is a metering device or a throttling device, to flash a liquid from a liquid state to a vapor state. So if you think of like a garden hose end where the water's coming through at, say, a pretty high pressure, but once it hits that end, right, we're releasing a lot of that pressure. We're partially vaporizing some of that water so we can restart the cycle within the refrigeration cycle. So we have 4 key components when we start understanding how the refrigeration cycle works. Number 1 is the evaporator, 2 is the compressor, 3 is the condenser, and 4 is that metering device that we just talked about. So let's start with the evaporator here. So evaporators look something like this. These are on different refrigerator units. But it's important to note that the evaporator is that entry point of heat from the external space into the system. So the heat that comes in from whatever you're trying to cool, it causes the refrigerant to boil. Remember, they boil at that low temperature. And once it once that boiled refrigerant leaves the evaporator, it should be 100% vapor by the time it moves on. And then that vapor is sent on to the next part, which is the compressor. The compressor we use to pump and compress the vapor. So we're increasing the refrigerant temperature and pressure by pumping it, right, and adding pressure to it. So as you increase the pressure, you increase the temperature. So it creates and maintains pressure differential within the system, because we also have to release that pressure on the opposite side of the cycle. But what we're doing here is we're turning that low pressure vapor into a high pressure, high temperature vapor. And that refrigerant temperature must be raised above the ambient temperature to give off the heat and to condense. So whatever your ambient temperature is outside the unit, say it's 70 degrees, we have to be able to raise that refrigerant temperature above that in order to give off the heat. So this is what some different compressor examples look like in different applications. The next step is your condenser. Just like your evaporator was the entry point for heat from the external space, your condenser is the exit point for heat leaving the system. Okay, so this is where we actually take the heat out, and what it does, it cools the vapor. Once we cool it, it condenses it back into a liquid, and then so we're de-superheating, right? We're taking it below its boiling point. We're condensing that vapor into a liquid, right? And then we're also subcooling it at that point as well. And condensers would look something kind of like this. After the condenser, we hit the metering device or throttling device, right? And all this is basically an expansion valve. And this controls the flow of refrigerant within our system, and it flashes that liquid to a liquid vapor mixture to restart the cycle. And we're turning that high pressure liquid into a low pressure liquid, and turning that warm liquid into a cold sort of vapor mixture. So as we are reducing the pressure on that liquid, it is cooling the liquid as well, and then we're going back in to start the cycle. And this is what some different metering devices would look like. So if we put it all together, we have the evaporator, compressor, condenser, and metering device, right? So our heat comes in this way. We have now a low pressure, low temperature vapor that leaves your evaporator. Remember, it has to be 100% vapor at that point for the compressor to work. The compressor turns that vapor into a high pressure, high temperature vapor to send it to the condenser. This is where we eject the heat from the system, which causes the refrigerant to cool and condense, turns that high pressure, or turns into a high pressure, warm temperature liquid. Okay, so now we are going from vapor into liquid here. And at this point, we have the metering device that turns our high pressure, warm temperature liquid into that low pressure, low temperature liquid vapor mixture. We also look at our refrigeration cycle as both a high and low pressure system, right? So same general concept. We have the heat here. We have low pressure on this side. We have high pressure on this side. So if you draw the line, high pressure side, low side pressure. We look at it from inside the system versus outside the system as well. So our evaporator is inside your system, generally speaking, right? Your compressor and your condenser are outside the systems, where we're taking the heat out, and then your expansion valve is taking it back in. And then we have a liquid versus vapor side. So we can split the system this way too, where we have vapor side down here, and we have liquid side up top. So I can let you guys go through all this stuff on your own as well. Don't need to burden you with it. Just showing how the refrigerator works. Same holds true for how we cool a building. Just a different process, because we have to use things like chillers and air conditioning units, or air handling units, and we have to use cooling towers potentially, depending on the system design. But it does the same general thing. So I'll let you guys look through these ones, how your air conditioner would work. Within a house, right? So we have our condensing unit outside that is ejecting the heat, and we are taking the heat from in, pulling it out, sending that cooled off air back through. Why it's important to also understand then how, going back to the sensible versus latent heat, right? If we have a pot of boiling water, it will not change temperature as long as the liquid still exists in there. This is the same thing for the refrigerant, right? So this is why we have to superheat things and subcool things. So what this all means is until that refrigerant changes state 100%, it will not change temperature, right? So if the refrigerant is changing state, it is considered saturated, right? So then the pressure temperature relationship holds true. We can predict the pressure given at any certain temperature, and we can predict the temperature given a pressure because of how the change of state has to take place in dealing with latent heat. So this chart right here is just kind of showing how sensible temperature works with latent temperature. And we're measuring that latent heat in BTUs, measuring sensible temperature in degrees Fahrenheit for this graph here. Oh, let's see. So this one is animated. So at this point here, we have 0 degree Fahrenheit ice, right? As it's picking up temperature going to 32 degrees, we still have ice all the way through here. But at that point, we need to change the state of matter. So we maintain 32 degree Fahrenheit water, right? But at that point, we're adding latent heat to change the state of matter. Once we do that, it becomes water, right, at 32 degree Fahrenheit water. Again, adding the temperature, get us up to 212 degrees Fahrenheit. Obviously, this is not to scale. But at that point, again, we need to boil it 100%. So until it's boiled 100%, we have 212 degree water, turns into 212 degree steam. So anything we add after that is superheated steam. All right, so this is roughly 144 BTUs per pound, and this is roughly 970 BTUs per pound of latent heat at that matter change. Same thing with subcooling. I'll let you kind of go through that on your own as well, just kind of showing the same in reverse order, but a little simpler because we're only talking at that boiling point. And we talked about these as well. Oh, animation's off a little bit. So why we use this, right? Superheating ensures that the refrigerant is entering at 100% vapor as it's going into the compressor, right? More liquid boiling in the evaporator absorbs more heat, so we need to compromise. So at that same point, then we have to subcool to increase performance within the system. So this allows for cooler liquid entering in the metering device, right? Then we have the flash gas, which is also the small amount of vapor that's resulting from the action of the metering device. So it allows for the remaining liquid to boil, a necessary efficiency loss. We can't maintain 100% efficiency. Obviously, that's not really possible. Laws of physics don't allow it to happen. So we have to lose something as we're going through and pick up heat as we go. So the balancing act between the subcooling process and the metering device and the superheating process going into the compressor helps balance the system and maintain efficiency or increase efficiency. We also have refrigerant lines within our system too. We have a discharge line, which is on your high side. We have a liquid line, which is on your high side, and we have a suction line, which is on your low side. So these different lines come into play again within the cycle. We have our discharge line over here. We have our liquid line over here, and we have our suction line over here. And I think that's the fastest I could possibly get through that one. No, I tend to get a little bit lengthy. I do want to pull up, though, for you the superheat and subcooling measuring really quickly as well, even though we're not really going to go into that in too much depth. Sorry, I'm at the end of the slideshow here. But what it's showing is basically how we calculate them, and all the different refrigerants that we use have their own pressure temperature chart. So they're already pre-calculated. You just have to know how to read the chart. Again, more for HVAC technicians, not something that I honestly ever had to do as a project manager. But to measure, we have to find low side pressure, right? So going back to the refrigeration cycle, understand the low side pressure, converting it to its saturation or boiling temperature. So we measure the suction line temperature with a thermometer. We superheat it. That superheating equals suction line temperature minus saturation temperature. So the way you would look at that is, so an example here, we have R12, which is a refrigerant. It has a low side pressure of 21 psig and a suction line temperature at the outlet of the evaporator at 23 degrees Fahrenheit. And what is the evaporator superheat? So the solution, we would have to look through and use this pressure temperature chart here on our right. So we're looking at 21 psig for the R12. Okay. Temperature is about 20 degrees Fahrenheit. So we take this outlet temperature, or the suction line temperature at the outlet, I should say, which is 23 degrees, subtract 20 from it, which is this number right here, and you have 3 degrees Fahrenheit of evaporator superheat. Same general concept for subcooling, but a little bit different. We have to use the saturation temperature and subtract the liquid line temperature for that one. So we have to find the high side pressure, convert it to its saturation temp, measure the liquid at the line, measure the liquid line temp, and go that route. So different refrigerant here, R404A. We have a pressure of 218 psig on the high side, a liquid line temperature of 85 degrees Fahrenheit. What is our system subcooling? So we have to look over here and find 218, which is down in this area. Convert that to condensing temperature is about 95 degrees Fahrenheit. Okay, so we have 95 then, right, minus our 85, which we know from our liquid line temp, and that just comes out to 10. So that is our subcooling requirement. And this is just an animated video here, or slide here, showing kind of how your refrigeration cycle works within the different components. So again, you guys will have access to that so you can see where all this is as you look through the system. All right, next and last, we have refrigerants. So 3 major categories: CFCs, HCFCs, and HFCs. This is not my area of expertise, but I do know that CFCs are no longer really utilized anymore. I think they have been banned in most places, if not all. They were heavily replaced by the HCFCs because of the depletion of ozone surrounding it. HFCs are now your most common. This is what I've seen primarily in any of my career, are HFCs as we're building new facilities. But you will still see these things in older facilities potentially. And your refrigerants here are just kind of showing we have, they're color coded as we're learning how, or as you're learning what different refrigerants we're needing for projects. They're labeled with R's, indicating that they are refrigerant. Again, I'm not expert in this category here, so I'll let you guys read through this, but we have different trade names for them. I do know that I've used a lot of Freon and glycol on different systems. A lot of them are blends from different refrigerants. So this example here would be an R124, an R142B, and an R22. A combination of different chemical components of that would create a R409A, which is one of the different type of refrigerants that are commonly used. So with that, I will leave you again. Make sure if you have any questions, let me know. These last things down here are just different websites that provide additional resources for understanding differences in latent versus sensible heat, how the AC units work with the refrigeration cycle, and then explaining in a little more depth superheating versus subcooling. And I'll leave you to it.